And here we are in the Bio 104 lab up on the second floor of the science building. And what I want to do today is show you some ideas about concentrations and dilutions and solutions and moles and molarity, some exercises I did with my freshman lab this week. So we'll get started. We'll be talking about sugar quite a bit today, but I also want to talk about something called moles and molecular weight. We'll get to that in just a minute. And let's begin with a quick rundown of how we measure weights in extremely tiny particles, things like protons and neutrons and atoms and molecules. The tiniest weight that we deal with in chemistry is called an atomic mass unit. It's 10 to the minus 24 grams. That is a very tiny weight. It turns out that the hydrogen atom, the simplest of all atoms, is about 1 atomic mass unit in weight. A carbon atom is 12 times heavier. It weighs 12 atomic mass units. The nitrogen atom weighs 14 atomic mass units. The oxygen atom weighs 16 atomic mass units. And by the way, these are all very lightweight molecules. In the chemistry of life, we're dominated by very lightweight elements in biochemistry. Now, once we have our atoms accounted for in individual weights, we start combining them and build molecules. For example, we can take a carbon atom and 4 hydrogens. That would be 12 for the carbon, 1 each for the hydrogens. And methane, a simple gas, weighs 16 atomic mass units, very common natural gas. Ammonia, very slightly heavier, nitrogen atom and 3 hydrogens for 17 atomic mass units. Water, our old friend H2O, weighs 18 atomic mass units. Again, these are very lightweight chemicals. Carbon dioxide, CO2, weighs 44 atomic mass units. And now we get into 2 interesting biochemical molecules, glucose, C6H12O6, known commercially as dextrose. Very common sugar, ubiquitous in life. It weighs 180 atomic mass units. Not terribly big. The monosaccharide sugars are not large at all. And finally, a disaccharide sugar, sucrose, or cane sugar, table sugar as we know it, C12H22O11 for 342 atomic mass units. We'll keep track of these as we start building our moles and molarity concept in a minute. And we'll start with an example of comparing weights with some everyday items that we're familiar with. On the left side, we see an ordinary standard metal paper clip. It weighs approximately 0.35 grams. It's about 1/3 of a gram. It would take 3 of these paper clips to make up 1 gram in weight. On the right side is a large glass pipette. We'll be using this later in our molarity example. And it weighs 15 grams, so it's quite a bit heavier than the paper clip. And now let me use an ordinary example we're all familiar with. I want you to imagine 1 dozen, 12 items, and ask the simple question, what weighs more, a dozen paper clips or a dozen glass pipettes? Remember the paper clip, about 1/3 of a gram in weight, the glass pipette about 15 grams in weight? Not even close. A dozen paper clips weighs much less than a dozen pipettes. But what's interesting about both of these is that they have the exact same number. So a dozen is a measure of a number. A dozen paper clips, a dozen pipettes, a dozen elephants, a dozen mice. For example, what weighs more, a dozen elephants or a dozen mice? Silly question, but they both have the same number of items. Keep an eye on that idea. One of the things I want to do in a minute is talk about molar concentrations. And we need to talk about a standard volume. So I have 2 standard volumes liter measures here. On the right side, liter flask holding a liter of water. On the left, a graduated cylinder holding a liter of water. We're going to be using these as standard volumes in a minute. So let me set this up for you. The reason we're concentrating on moles here, no pun intended, is that like a dozen, a mole is a particular number of items. There are 6.02 times 10 to the 23rd particles in 1 mole of any chemical. And you're wondering, my God, whoever came up with a calculation like that? Well, an interesting Italian physicist in the early 19th century, Avogadro, came up with this calculation. He was dealing with volumes of gas. I don't know how to express this in any sensible numerical term, but 6.02 times 10 to the 23rd particles, we'll call it roughly 6 gazillion particles. Now, why is this of interest? Well, let me show you a way to compare something here. 1 mole of glucose weighs 180 grams. If you dissolve it in 1 liter of water, you'll have a 1 molar solution of glucose. 1 mole of sucrose, 342 grams of sucrose, dissolved in 1 liter of water would give you a 1 molar solution of sucrose. Even though the sucrose solution weighs a lot more than the glucose solution, they have exactly the same number of particles. There are 6 gazillion particles of glucose and 6 gazillion particles of sucrose suspended in the 1 liter in each solution. And that's the beauty of using moles and molarities in measuring concentrations. And what I've done here is I've gotten out our reagent grade of sucrose, ordinary table sugar, again C12H22O11, and perched delicately up here on balance is approximately a rounded teaspoon. And what I've done is I've used our Mettler balance to weigh out how much sugar is in a rounded teaspoon, and it works out to about 8 grams. So the weight of 24 paper clips, or the weight of half of those pipettes, one of those pipettes, and that's approximately 1 rounded teaspoon of sugar, and we'll use that in our coffee exercise in a few minutes. Now what I've done here is I've taken our reagent sucrose and I very carefully weighed out 342 grams of sucrose. The reason I chose that weight, it happens to be exactly 1 mole of sucrose, 342 grams. It's about 2/3 of a pound of sugar. That's quite a bit of sugar. Now, if you were to dissolve all of that sugar in 1 liter, and again, these are the liter standards that we've been using, dissolve that much sugar in 1 liter, you would have a 1 molar solution of sucrose. It would be very thick, it would be very syrupy, it would be incredibly sweet. Probably a lot sweeter than the way you would ordinarily drink your coffee. We'll get to that example in a few minutes. Now here we are with a 1/4 liter volume. This is 250 mLs of water. I want you to imagine it's about the size of an ordinary cup of coffee. Your typical cup of coffee, about 250 mLs or a 1/4 of a liter. So let's set this up. If we put 1 teaspoon or 8 grams of sucrose into our 1/4 liter cup of coffee, that's the typical amount you would have in 1 teaspoon of sugar dissolved in a typical cup of coffee. Now, follow the calculation here. What we're going to do is 8 grams divided by 250 mLs is equivalent to 32 grams divided by 1,000 mLs, so they are the same concentration. Now, 342 grams of sucrose dissolved in 1,000 milliliters would give us a 1 molar solution. So if we set up a quick equation, cross multiply and divide, a teaspoon of sugar in your morning coffee is equivalent to 0.094 molar solution of sucrose, or about a 1/10 molar solution of sucrose, roughly, which means a lot less sweet than that syrupy 1 molar solution that I set up for you for a few minutes ago. Just roughly an idea of how we use molarity to estimate the amount of sugar in a solution. And we could convert this and find that we have about 1/10 of 6 gazillion particles of sucrose in that coffee. Now what I'm going to do here is try and set up a visual display of how concentrations vary when you're using 1/10th dilutions, 100th dilutions, 1,000th dilutions, and so forth. We're going to do some diluting, and on the far left side I have 5 mLs of coffee, and the other 3 cylinders to the right all have 4.5 mLs. I know it doesn't look like the same amount because there are different diameters in these tubes, but there are 5 mLs of coffee on the left, and the 3 remaining cylinders have 5 mLs of water. Now in a minute what I'm going to do is show you how to do a 1/10th dilution, a 100th dilution, and a 1,000th dilution. I'm going to be kind of a one-armed pipetter here, so bear with me for a minute. Now I'm ready with my pipetter, and I've got the pipetter set so that it will draw up 0.5 mLs or half a milliliter of liquid. And so what I'm going to do is plunge down, and I'm going to come in and take a half of ml of coffee. I'm kind of shaking here. There's a half ml, And I'm going to place this in 4.5 mLs of water, like so. And then I'll get rid of the tip because I'm not going to reuse this tip. We'll come over and get another tip because I'm going to do another serial dilution in just a second. We'll bang this out. I'm going to put the pipetter down for a second. Now think this through. We had 5 mLs here, and we add a half ml to 4.5 mLs of water. So this is now a 1/10 dilution of this solution. If this was a 1 molar solution, this will now be a 1/10 molar solution. You with me so far? Now let's do the same thing again. We're going to take another half ml out of the 1/10 molar solution and place it in 4.5 mLs of water, like so. And we'll dump this tip. We'll come back and get another one because we're going to do one more dilution here. Let's put the pipette down. Now again, follow what we're doing. A half ml out of the 1 molar in 4.5 mLs of water will now give you a 1/10 molar solution. A half ml of the 1/10 molar in 4.5 mLs of water will give you a 100th molar. And now let's do the final dilution. Now we're going to go down to the millimolar level. I'm really shaking here because I'm a one-handed pipetter today. And in here, boom. And let's get rid of the tip. And again, let's think this through. 1 molar, 1/10 molar, 100th molar, and 1,000th molar, or millimolar, and you can barely see any color. So look at the step down that we've done. 1 molar, a 1/10 molar, a 100th molar, a 1,000th molar, millimolar concentration. You can see there's hardly any of that coffee in there. It's very, very, very diluted. And this is an interesting example. If you think about how much blood sugar we carry, we've been talking about sugar in the coffee. Normal human adults, we carry around 4 to 6 millimolar concentration of glucose in our blood. We take a very, very, very tiny amount of sugar through our day. We don't store much sugar at all. And it gives you an idea of some of the problems you run into in diabetic conditions where individuals can lose control over the regulation of their blood sugar. We actually store incredibly tiny amounts, millimolar concentrations of sugar in our blood in day-to-day activity. And there you have it. I hope you enjoyed this presentation I made on molarity and concentrations. It mimics some of the things I did in my Bio 104 lab earlier this week. And so now I can sit back and enjoy my cup of coffee. This is decaf coffee, Mr. Excitement. But I don't drink any sugar in it. So sugarless decaf coffee. I hope you enjoyed it. Thanks.